This is a lesson about relative motion in the kinematics unit. The first aspect we need to talk about with relative motion is the idea of reference frames. And a reference frame is broadly defined as a set of 3D axes in a clock. Okay, so you're sitting wherever you're sitting or standing or laying or whatever, right? And you have a 3D environment with you, and you have a clock, and wherever you go in there, that's your reference frame. And things can be at rest in your reference frame, or things could move in a reference frame. You could move in your reference frame. Okay. Often we think of this in terms of the ground or the earth. This is how humans typically experience motion, is that the ground is stationary, and that's our reference frame, and everything is measured relative to that, and we all have in a common reference frame so that we can all communicate well within it and agree on things that are measurable in that reference frame, such as distances and times. Okay, a moving frame containing an observer may be an example of a person on a train or a person in a car. If you've been in a car, this is a familiar thing, that you could be in the car moving, and if you consider the car your reference frame, you're not moving in your reference frame. You're sitting in that reference frame, and things are moving around you. You can have a moving reference frame. And so there's this idea of there's different reference frames. What is the preferred reference frame from which to measure things? And here is the thing about the cosmos, is that there is no absolute reference frame. Okay, everyone experiences what the physics in their reference frame at all points across the cosmos in all the rules of physics that we assume. That's the assumption of reference frame. And really what matters is the relative speed between two different reference frames. So if you're in a car and that's relative to the ground, those are the two reference frames. And the one reference frame has a speed relative to the other. Okay. I find that it's common for people to never think about reference frames in that formal way and have an intuitive or instinctual idea of reference frames in general. I think it just comes like in our experiences or programmed in that this is an idea that feels very easy to catch on to, and the challenging part is formalizing it. How can we formalize this idea into science? So what we see with reference frames is that observers in different reference frames moving relative to one another will measure the same event differently because they're in two different reference frames. And this is what we call relative motion. And when we look at this comes down to the strategy for formalizing this will be vector addition. It's just addition of velocities. Velocity is a vector. We have three objects and three velocities, and we can just set up a vector equation, okay? The challenging part of this, and this is why this is often kind of skipped over, glossed over in many physics curricula, is because it's challenging to figure out at first, but once you figure out how to solve these problems, they're not too bad. It's addition of vectors. The key here is to consider three different objects in the equation that create the objects and the reference frames. Okay, and I picked tree, car, ground as a good example because, like I was saying before, this is kind of instinctual for a human being to think about on the planet. Okay, so three objects are necessary. So when you are in a car, and you see a tree and the car is moving, the tree will move by in the negative direction. We can all agree on that. We also know that trees don't move. Trees are rooted. They don't move relative to the ground. So the fact that the car is moving forward can tell us that overall the tree is not moving because we're measuring the velocity of the tree from a moving reference frame. There's a relative motion in there. And the trick here is to think about this in two different ways. I like to think about this in two different ways. There's a numerical right? We're going to figure out a number here. We can figure out a number. And another way to represent this, and remember representations help us with the formalization, and that's why we have vectors. Again, this is in a vector equation. Okay, so let's put this together. I want to say that, let me find out the velocity of the tree with respect to the ground. And that's a clever thing to put on the C side of the equation because we already know it. The velocity of the tree with respect to the ground, when I think about the tree and how it moves with respect to the ground, it doesn't. So I know this is 0. And this is the numerical part of this question, right? I know it's at rest with respect to the ground. So what's going on over here on this other side of the equation? Well, notice that I'm inherently in here assigning my objects to these symbols. So let's write this out. A equals tree, okay, and C equals the ground. And the other object we have in there is the car, right? So B must equal the car. Okay, so let's write this information into our equation and then think about what that's saying. Velocity of the tree with respect to the car, and I'm going to put vectors over these because we have some vector things going on, the velocity of the car with respect to the ground. And maybe let's draw a quick little picture here. Okay, so here's the tree. We'll do a quick little tree here, and then we'll do a car. Let's see, am I drawing a car okay? There's a wheel and there's a wheel. There we go. There's a car, and the car is moving in this direction, room V of the car. And remember, this is the velocity of the car with respect to the ground when I'm looking at this, right? The car is moving with respect to the ground. The velocity of the tree with respect to the ground is 0. And I can write these things down. I already did that. The velocity of the tree with respect to the ground is 0. The velocity of the car with respect to the ground, and I can write G over here so you all can see that this is the velocity of the car with respect to the ground. Let's just say the car is moving, I don't know, a nice 25 miles per hour. That's a nice speed to go past a tree. Okay. And so plus 25. And I'm inherently assuming that this is the positive x direction, right? I have to assign a coordinate system. If I have vectors, I need to make sure I'm assigning a coordinate system so that I can have positives and negatives. Because when I think about it, let's fill in this part in here, and you see what this has to be in order for this equation to be true, is what is the velocity of the tree with respect to the car? That's saying make the car be the reference frame. Right? Because these two speeds, the ground is the reference frame. The second object is the reference frame. And the first object is what you're measuring moving in that reference frame. So we want to know what's the movement of the tree with respect to the ground. Well, we're going to look at the movement of the tree with respect to the car and the movement of the car with respect to the ground, right? We can measure it in a reference frame, but if that reference frame is also moving, we have to take that into account. Okay, so what is the velocity of the tree with respect to the car? Well, when I'm sitting in a car and going 25 miles an hour, I see myself at rest, and I see that tree moving backwards at the speed that is on the speedometer, right? So this has to be a negative 25. Do you see how that adds up to 0? So that's the magic of this equation, is you can kind of reason through the vectors of this equation. I like to draw a picture. Especially if you're working in 2 dimensions, you will need to draw a picture. Assign your coordinate system and really figure out what these 3 objects are. Another straightforward one-dimensional problem, and you notice that with the tree and the car, was that it was one-dimensional. So let's do another quick one-dimensional. You are planning a rowing trip along a river in the direction of a current. You know you average 5.2 miles per hour in still water and that the river's current is 8.6 miles per hour. How long do you estimate it will take to travel the 16 miles to your destination? Okay, well, traveling on a river is never very predictable, but we can do our best, right? So we're just estimating, okay? So I'm going to get a quick picture going here. There's a river. So I might draw, here's a river, and the direction of the current is in this direction, and I'll say it's at 8.6 miles per hour. And I'm even going to identify this. This has to be the velocity of the water, right? The current is water with respect to, well, we're measuring that with respect to the ground, the bank, right? We see the river going by, and that's the current, the velocity of the water with respect to the ground. And I've drawn that vector, and I've assigned its value, and I'm clear what the two objects are. So when I'm thinking about this equation, I'm seeing that I need another object. But of course, it's you in your raft, right? You're rowing, whatever you're rowing. You're there too. You're planning on rowing in the river. So you know you average 5.2 miles per hour in still water. Oh, words mean things. Let's think about this. So let's put you on the river. You'll be green, and you're in the river. I'll make your vector a little bit shorter because you cannot go as fast as the river. So the velocity of you, right? I'm not going to put another object in here yet, okay? The velocity of you with respect to something is 5.2 miles per hour. Well, you may be getting a feel already that you're moving with the current. The current's going to help you move along. These two vectors are going to add together. Let's remember to assign a coordinate system. This is the plus x direction, so that's pretty easy. It may seem not necessary now to assign a coordinate system. We're not working with too complex of a case, but the habit of mind to think I need to assign a coordinate system is going to be powerful as we move into more difficult problems. Okay, so we still need another object, right? So the velocity of u with respect to still water. The river is moving, so you can't say that 5.2 is like your velocity total, right? It's not with respect to the ground. Your velocity with respect to the ground is going to be both of those added together. So this velocity in still water, sometimes like if you're doing an airplane problem, they'll say with respect to still air or airspeed, they'll say something very vague, and that means it's without the help of any wind or anything like that. So this is u with respect to the water, and notice how I filled in a third object here. We have water, ground, and u. What we want to know, and if I'm filling out this equation, when I think about A, B, and C, what we really want to know is what is the velocity of u with respect to the ground. You probably already calculated it in your head, right? But we don't know that. That's our unknown here. What we do know is the velocity of u with respect to the water, which is the 5.2 in the positive x direction, miles per hour. And we also know the velocity of the water with respect to the ground, and that's the 8.6 miles per hour in the also plus x direction. Okay, so this is coming together. You can see the vectors. We're going to add these two vectors together. The velocity of u with respect to the ground equals the velocity of u with respect to the water plus the velocity of the water with respect to the ground. Okay. This is a vector equation. You can see how our two representations are cohering with one another. I have the numbers that I can fill in, right? 5.2 miles per hour plus 8.6 miles per hour. And I also have the vectors. My vector representations also correlate with this equation. So for me, these equations are not just like equations that you plug numbers into. They're much more powerful statements corresponding to concepts in the problem and quantities in the problem. And so I read them more like sentences. Okay, So the velocity of u with respect to the ground, we can calculate that. The velocity of u with respect to the ground is going to be 13.8 miles per hour, and that's in the positive x direction. But we already kind of knew that. We're being explicit. So did I answer the question yet? How long? No. Okay, so how long do you estimate it will take to travel the 16 miles to your destination? Okay, so let's find the time. We're rowing at a constant velocity. Remember, at constant velocity, I just do distance over time. So if I want to solve for time, you can do this on a side piece of paper if you like. It'll be the distance divided by the velocity. So I have 16 miles divided by 13.8 miles per hour. All right, and I can rewrite this so that you can see it's miles per hour. The miles are going to cancel. The hour is going to come up into the numerator, and I get 1.15942 hours. A little less than, or a little more than an hour. How to solve relative motion problems. Draw the vectors. I got that picture going, and it may even have been intuitive to do that, is to start drawing a picture. These pictures are powerful to help you solve the problem and to fill out your equations. So, assign a coordinate system and keep track of your signs. We had two positives in that problem, but you can see if you were trying to go against the river or across the river, etc. Which brings me to the next 2D. We're going to do some 2D problems where we're going to have motion in 2 dimensions. Okay, so our vector equation becomes a little bit more complicated. We can't just add vectors. We have to take into account x components and y components. So I will reference my vector addition video if you are having trouble with this still. So 2D vectors, we're going to divide the motion into x and y components, and notice that I put, it's the same equation, but we're going to isolate the x components separately from the y components. So we can do vector decomposition, deal with the 2 different dimensions, and then do vector resolution and bring them back together again if we need to. Always keep track of your signs, and my tip for the 2D is to use a chart, and I will show an example of that. The first problem I have is pretty straightforward. Practicing archery. Val is out practicing archery on a windy day. Val has impeccable aim and shoots an arrow directed at the center of the target at 320 feet per second. The wind, however, causes the arrow to drift off course. Determine the angle of deflection of the arrow's path if the wind speed is 22 feet per second perpendicular to Val's aim. Okay, so let's do this again. Let's get some vectors going. I'm going to draw the target. Boom, there it is. Let's see. Val, it seems like Val shot the arrow at 320 feet per second directly at the target and has impeccable aim, so it was right at the target. What we're being told is that there is a wind perpendicular to Val's aim. So whatever direction you want to put in here, I mean, we're going to assume maybe it's parallel to the ground. I don't see the wind blowing up or down, right? It's like parallel to the ground, but perpendicular to her. So that the wind is going to blow the arrow off course. And this is the 22 feet per second. This is why I say it's a little bit more straightforward of a problem, is that you can see in here that there is a right angle between these 2 vectors. So when we do vector addition, this isn't going to be too bad. Let's assign A, B, and C in our equation, right? We need 3 different objects. Let's think about the velocities we were given. This is the velocity of the arrow before any wind was taken into account. So what I will call this is the velocity of the arrow with respect to the air. Like if the air wasn't moving, the arrow would go this speed. Okay, so I've introduced 2 objects. Of course, this is not the velocity of the arrow with respect to the ground, which is what we're interested in, the velocity of the arrow with respect to the ground. That's what we're interested in. We don't know what it is, okay? We know the velocity of the arrow with respect to the air, and they also tell us the velocity of the air with respect to the ground. So this may feel familiar from the previous problem because we're filling out these 3 different objects, right? It kind of makes sense. And again, you can see how this vector equation is working for us. The velocity of the arrow with respect to the air, right? 320 miles per hour, or feet per second. And we're going to add on this wind. And this allows us to see the vector nature of this equation. We can't just add 320 plus 22 and have that be the answer. That is not how easy it is. We have to do vector addition on this. These 2 vectors are perpendicular to one another, so we're going to get this resultant velocity vector. This is what is going to be the velocity of the arrow with respect to the ground. And I'm going to note that I exaggerated this. These 2 vectors are not proportional. I made one kind of smaller than the other, but it's much, much smaller actually. Okay, but this is the velocity of the arrow with respect to the ground. It gets deflected off course. Okay, so we're asked to determine the angle of deflection. So we're asked to find this angle here. What is this angle? What is that angle? Well, okay, this is falling into place pretty easy. When I look at this angle, I know 2 sides of the right triangle, the opposite and the adjacent. Tan theta equals 22 over 320. If I want to find theta, I'll do the inverse tangent in my calculator, 22 over 320, and you get a nice 3.90 degrees. Pretty straightforward. And again, that picture was one of the keys to this problem. Right? There's no angles in here, but when I look at this picture, it's very clear what I'm calculating. If I wanted to finish out the calculation, if I wanted to find this, the velocity of the arrow with respect to the ground with that shorthand, and I wanted to find the magnitude of it, I would take the square root of 320 squared plus 22 squared, and that would give me the value of that speed, right? The velocity of the arrow with respect to the ground, if you run this through the calculator, is 320.75 repeating feet per second. So it doesn't throw the speed off very much. It doesn't throw the arrow off very far, but it's not at the bullseye when it gets there, and that's something to consider. So this is 2D vector addition with relative motion. Let's do another one just to be sure. Crossing a river, another river problem, and now we're crossing it. We're not going along the river, we're crossing against the river. So you can imagine that current affecting the motion differently. A boater wants to directly cross a river to arrive at a dock on the other side, and this is a problem that you will typically see in textbooks and on national standardized exams if you're moving that direction. The boat achieves a cruising speed of 15 miles per hour, and the current of the river is 8.6 miles per hour. At what angle must the boat orient itself in order to travel directly across? If the river is 3/4 of a mile wide, how long does it take? Okay, so at what angle and how long does it take? Very good. So let's get a picture going. Let's see what's going on here. Again, we'll have the 2 banks of the river. Let's get 2 banks of the river. And let's just say this is pretty standard to do, is I'm going to start here. So I'll put an I here for initial, and we want here to be the final. F for final. So I'm just going to draw a vector across here. And the powerful thing I can do right now is recognize that I need to identify the 3 objects. What are the 3 objects involved? Well, we have a boat, we have a river, and we have the ground. Okay, the banks if you want, but I call it the ground. Okay, so those are our 3. And when I think about this vector here is what the boat will actually travel with respect to the ground. If it wants to go straight across, that boat will go straight across with respect to the ground. Okay? If the boat did not take the current into account, it would drift downstream, and this would be the final down here. That's not what we want. We want the velocity of the boat with respect to the ground to be this straight line across. That's how it will get there. Okay? What it will need to do is orient itself up the river in order to counterbalance the current pushing it down the river. Right? That makes sense. In order to counterbalance, you have to go against the current. And if you go against the current as much as the current is pushing, then it'll go straight across. Okay? So that gives us our other two vectors. If I point the boat into the current the whole time, the current will push back down the river, and I will end up at the boater will end up at the final point right here. Okay, so let me fill in that. I was talking about it, but I didn't fill it in yet. So this is going to be the velocity of the river with respect to the ground. Whatever you want to call it in there that makes sense for you. Velocity of the river with respect to the ground. It goes straight down that way. Okay. And then this, it has to be the velocity of the boat with respect to the river. And this will seem weird. I'll give you a moment to think about this. We can think about it together. While the boat is crossing the river, the whole entire time, the boat won't travel this and travel that. That's not what happens. The boat does not travel those two vectors. The boat goes straight across. The velocity of the boat points in that direction. So as it goes across the river, that boat will be oriented into the current the whole time as it travels across there. Does that make sense? It points its motor into the current that whole time, and it ends up going straight across. So let's get the equation into it. I need to assign a coordinate system. We'll just do standard, and this is fine for me for a coordinate system, 2D. I am clearly pointing out which direction is the positive x and which direction is the positive y, and I can see that the velocity of the boat in the river is going to be at an angle. So let me assign an angle in here. I will assign theta to be this. Theta. Okay. So, and this will be where we use a chart. Let's get the equation together. The velocity, I want to know the velocity of the boat with respect to the ground. That has to be equal to the velocity of the boat with respect to the river, plus the velocity of the river with respect to the ground. And we already kind of see that equation happening in our vector diagram here. All of these vectors are added together appropriately. Okay. Let's use a chart. This is how you would use a chart in this situation. I create an X and Y column. And I create, in this situation, we have three objects. We're going to have the velocity, or three velocities. The velocity of the boat with respect to the river. I'm going to add on the velocity of the river with respect to the ground. And when I add those together, the final thing I get is the velocity of the boat with respect to the ground. And if you remember the x, y equations I had on one of the previous slides, you will see that this is the final in the x and this is the final in the y. And what I know is the velocity of the boat with respect to the ground has no x component. Do you all see that? It has no x component. We want it to go straight across. So the velocity of the boat with respect to the ground will be 0. Let's see. Let's divide that, the boat with respect to the river. Let's divide it into two different components. All right, let me get this out of here. Velocity of the boat with respect to the river. we can have an x component there and a y component there. We can see its x component is a negative value. And when I look at it, its value is 8.6. Nope, 15. And it is the opposite leg from our angle, right? If this is theta here, this is also theta here. It is the opposite leg. So I'm just going to put in here 15 sine theta. That's the component of that right triangle here, that from the 15 and the theta. It has a y component. I'm going to go ahead and put the y component in here. The y component is the adjacent leg, so it has to be cosine, and it's in the positive y direction. So plus 15 cosine theta. Remember, I don't know theta. What angle? At what angle must the boat orient itself? So we're finding the angle. Let's do the other one. The velocity of the river with respect to the ground. It is only in the x direction. It has no y component. So in the y direction, I'm going to put a 0 here, and it is 8.6. It's just 8.6 in the x direction. So that's how I would use a chart to add this up. When I add up, I know the velocity of the boat with respect to the ground is going to be plus 15 cosine theta. If I wanted to find the value of that, if I knew theta, I could just find it. But I need to find theta, and you can see that's what's happening here. If I isolate this equation in the x direction, I get 0 equals negative 15 sine theta plus 8.6. And I can find theta. This becomes a linear equation where I can solve with an inverse sign, right? 15 sine theta equals 8.6. Sine theta equals 8.6 divided by 15, and I can pop out theta. Theta equals the inverse sine of 8.6 over 15, and when you plug that into your calculator, you get 35 degrees. Let's solve part B. If the river is 3/4 of a mile wide, how long does it take for the boater to cross? Okay, so we want a time, and I'll do this over here. To find the time, it's constant velocity, again, so we know velocity equals distance divided by time. We can do some algebra on this and see that the time will be the distance divided by the velocity. Okay. So the distance will be, well, it's 3/4 of a mile across, 0.75. And then the velocity that it's moving across the river, remember across the river is in the y direction, and it is the final velocity of the boat with respect to the ground, 15 cosine theta. So 15 cosine 35 degrees. You can see that we can pop out a number right from that because we know theta now. When you calculate this, run this through the calculator, you get t equals 0.0610 hours. All right, good. Let's put this in a comprehensible time. Turns out this is 3 minutes, 3.66 minutes. So 3 2/3 of a minute, about 3 minutes and 40 seconds to cross a river 3/4 of a mile wide at whatever speed it's moving at, 15 cosine 35. So just to reflect, go back over this problem. The time seems reasonable. It's 3/4 of a mile at 15, something less than 15 miles per hour. We wrote out our diagram and got our 3 vectors going. Notice that we have a vector equation, so we're going to have 3 vectors because of the 3 vectors in the equation. And we use this chart here in the x direction and the y direction in order to set up equation in the x direction separately than the equation in the y direction. This allows us to separate the motion.